Hi, everyone. This work that I'll be talking about concerns the complexity of non-local games, games that involve quantum entanglement. So, just before I talk about our results, I should first lay down some definitions. I should describe, what non-local games are. So, in a non-local game, you have two players that can't communicate. We usually call them Alice and Bob. And in a non-local game, it's parameterized by two objects. One is a joint probability distribution, pi, and a verification predicate, v. So to play this game, these two players will interact with the referee, or a verifier. And the verifier will sample a pair of questions, x and y, from this distribution pi. And the verifier will send x to Alice and y to Bob. And they have to respond with answers A and B. And the verifier will check if they have won the game by evaluating the predicate v of x, y, a, b, and see if it's won or not. So perhaps maybe the most well-known example of a non-local game is a CHSH game. Probably many of you have seen it before. And in this game, the verifier will exchange bits with Alice and Bob. And it's well known that in this game, the classical value of the CHSH game is 3/4. So this is when Alice and Bob use a classical strategy to play the game. Okay, the best they can do is to win with probability 3/4. But if they use quantum entanglement, they get access to more powerful correlations, which allow them to win the game with probability strictly greater than 3/4. It's about 85%. And we use the notation omega star of CHSH to denote this optimum winning probability. And the CHSH game is one of the most important classical tests of quantum behavior. So it's an example of a Bell test that you can use to check for non-local behavior. It's crucial in device-independent quantum cryptography. And it's also used to do delegated quantum computation. So non-local games have many applications in quantum information. So the motivating question of this talk is a complexity theory question, which is we want to know what's the complexity of this problem. Given a k-player non-local game, so the game that I talked about before, the CHSH game, is an example of a two-player game, but we want to consider games with any number of players. We want to compute what is the optimal success probability for players sharing entanglement. What's the best they can do in a quantum world to play a given game G. And the complexity is a function of the number of players, k. It's a function of epsilon. So in this problem, you want to approximate the entangled value, plus or minus epsilon. And it's also a function of the game G, the description of the game G. And here, we think of the game G as being presented explicitly. So imagine that to describe this game, I wrote down on a piece of paper the joint probability distribution pi, and I also write down the verification predicate v as a truth table. Okay. And here I'm going to formally define what the entangled value is. So for a game G, omega star of G is an optimization problem. So it's you take the supremum over all possible entangled strategies for, let's say, we're talking about two-player games for Alice and Bob. Okay. And what does an entangled strategy consist of? Well, first you have to pick a dimension d. Okay, it's an integer. And you pick an entangled state, a bipartite entangled state with local dimension d. And finally, for both of the players, you pick sets of measurement operators that they apply. So, when the referee samples a pair of questions, x, y, the players will make measurements depending on the questions that they receive. And this expression evaluates what's the probability that they output answers that satisfy the predicate. Okay. So this is kind of a crazy optimization problem. One of the biggest challenges is that to try to evaluate this number is that there's no a priori upper bound on the dimension D needed to win any particular game, right? So if I gave you a game G and I asked, I want to know what's the best possible strategy for this game, what's the minimum dimension do you need? There's no general answer that we know of yet. And so what this means is, even if you just wanted a brute force algorithm to try to estimate this number, we don't know of any. Okay, so so this question of what the complexity is, it's very interesting. So why study this question? There's a lot of motivations for understanding the complexity of non-local games. So the first thing is, we'd like to understand, the set of quantum correlations. Are there nice mathematical characterizations of this set? People have been trying for years to get a handle on it, and this complexity question is a nice avenue towards approaching it. From quantum complexity theory, we'd like to understand this question because it's very closely related, and in fact directly related to this question of the computational power of the class MIP star, which stands for, it's the class of all problems that you can solve using multi-prover interactive proofs where the provers share quantum entanglement. Okay. There are applications to quantum information theory and cryptography. Oftentimes people would like to code up algorithms to try to optimize over the set of quantum correlations. And in general, we don't have algorithms to do this very well. Oftentimes we just write down an STP or a hierarchy of STPs and hope it works. And there are also connections to some deep areas of mathematics. So the computability of this entangled value of games is implied by positive resolutions to questions that we don't have the answers to yet, such as Sirelson's problem and this problem known as Kahn's embedding conjecture, which comes from the theory of operator algebras. Okay. All right. So let me state our main result. So our result says, for all k greater or equal to 4, so k is the number of players, for all functions f of n that's greater than n, the problem of determining whether a k-player non-local game G satisfies omega star of G as being equal to 1, meaning that there is some strategy that allows 4 or more players to win this particular game with 100% probability, or the success probability is at most 1 minus, let's say 1 over f of n. Okay. Promise that this one of the two cases is satisfied. The problem of determining which one's the case, this requires 2 to the f of n time, even if you're given non-deterministic resources. Okay. So there's some fine print to this result. One is this doesn't actually hold for all possible functions. So f of n must be what time computable, but essentially any natural function that you can think of. So a useful thing to keep in mind would be, think of f of n as being, say, 2 to the n or 2 to the 2 to the n, or any tower of exponentials. And also, so our result holds for 4 or more players, but we think it also holds for 3. Okay, so that's our main result. And I should also mention some concurrent work that's very closely related, so I'd like to show this. So this is a result due to Matt Kudron and William Slofstra. And it's very similar, but in some sense it's kind of incomparable. So it's also a complexity lower bound on the problem of computing the entangled value of games. So the result holds for all f of n. It holds for 2-player games. And it holds for something called the commuting operator value of the game. Okay, so that's denoted by omega to the CO. And their complexity result is, the problem of distinguishing between these two cases is hard for co-non-deterministic time f of n. Okay? And this was proved using very different techniques. They use these group theoretic techniques that come from earlier works of William Slofstra and Richard Cleve and so on. Okay, so let me place our result in the context of some prior results. So, people have been studying this question of the complexity of non-local games for many years, and so I won't give an exhaustive list of what's been proven, but here's sort of the relevant recent results. So the complexity results that people have proven are a function, the people prove different results depending on the type of accuracy you'd like. Okay, so one recent result, which is due to Natarajan and Vidic, is that if you want to estimate the entangled value of games up to a constant, say plus or minus a half, it turns out that this is QMA hard. Okay, meaning that if you could solve this problem, you could say estimate the ground energy of local Hamiltonians, and this result holds for 7 or more players. And this is also known as the quantum PCP theorem for entangled games. So if you want to estimate the entangled value of games up to a tighter accuracy, say 1 over polynomial in n, and I should say what n is the size of the description of your game. Okay? So if you want accuracy that gets better as the size of your game gets bigger, then this turns out to be nx hard. Nx is the exponential time version of NP. And this was proved by Zhengfeng Ji. And on the other end, William Slofstra proves that if you want to compute the entangled value of games exactly, this is actually an uncomputable, this problem is undecidable. So if you want to know whether a given 2-player game has a perfect strategy or not, there's no algorithm to do this in general. So if you squint your eyes, you can sort of see that it seems like as you ratchet up the accuracy, you want to have better and better accuracy, this problem seems to get harder and harder. At least that's the, as far as our lower bounds go. And what our results show, and what the results of Kudron and Slofstra show is that basically it sort of interpolates between these first 2 results and Slofstra's undecidability result. So as you want to get better and better approximations to the entangled value, the problem just gets harder and harder. Okay, or at least we can show that it just strictly requires more and more time. And also as a corollary of our techniques, we give a different proof of Slofstra's undecidability result. Okay, so now I'm going to sort of get into the main technique behind how we prove our complexity lower bounds. And it comes through this notion of compression of quantum games. Okay, and it's a very general technique. So the technique basically says, given a general quantum game G, we can efficiently transform it into another game G prime that's exponentially smaller. But the game is in some sense equivalent to the original game. Okay. So let me be more precise. The main technical theorem that we prove is a composable compression theorem. And it says, there exists a polynomial time transformation such that for all k greater or equal to 4, this transformation takes in as input a succinct encoding of a k-player non-local game where the verifier runs in polynomial of n time. Okay. And the output of this compression scheme is another k-player game, G prime, where now the verifier runs in logarithmic time, log of n time. And the entangled value of this new game G prime is related to the original game's entangled value in the following way. If omega star of G is 1 minus epsilon, then omega star of G prime is closer to 1 by a factor of poly in n. Okay, so remember poly in n is the complexity of the original verifier. Okay. So in other words, this compression theorem gives you a way to shrink games, to shrink the verifier of games at the cost of shrinking the gap of your game. So by gap, I mean how close the value is to 1. So once you have this theorem, it should be somewhat intuitive how you can use such a compression theorem to prove our complexity lower bound. So as an example, let's run through how we show that distinguishing between entangled value equal to 1 or at most 1 minus 1 over f of n is hard for non-deterministic time 2 to the f of n. And for concreteness, let's think of f of n as being doubly exponential in little n. Okay. So at the highest level, the proof idea is the following. So I'm going to use this elephant to represent verifiers or a quantum game. So it turns out that for this ridiculously large complexity class, non-deterministic time 2 to the f of n, right? So this is triply exponential non-deterministic time. There is a non-local game that you can construct that will decide languages in this class. Okay. But the issue here is that this game is so large. It's doubly exponentially large. Okay. And so this is not, we'd like to shrink this verifier down. And so using our compression theorem, you can shrink this game to one where the verifier, sort of decides the same language that you started with, but now it runs in singularly exponential time. And then you just run this compression scheme again, and you finally get a polynomial time verifier. Okay. So that's the general idea, and it makes intuitive sense. So let me skip these details. Okay. So this composable compression theorem is based off of an earlier protocol compression result of Jiangfeng Ji. Let me put it up here, and it should look very similar to the theorem that I mentioned a couple minutes ago. But there's a couple key differences. So the first difference to notice is that it takes in a game G and it outputs another game G prime. The guarantee about this output game G prime is that the verifier, the questions that it sends are of logarithmic size. But there's no guarantee about the complexity of the verifier itself. Okay. So in fact, the verifier that's produced by this compression scheme, the time that it takes to run is still poly of n time. So at least in terms of time complexity, it hasn't gotten any smaller. Okay. So that's one difference. Another big difference is that the game that's output has more players. So if you started with k players, it gives you a new game with k plus 8. Okay. And you could try to, even if you didn't have this first problem of the verifier not shrinking in terms of time complexity, if you try to iterate this game too many times, the number of players would blow up. So let me give just sort of a bird's eye view of what goes into this compression theorem. And the compression theorem we prove is largely based off of the same idea. So what happens in this compressed game G prime? What it does is it checks whether the players, so you started with a game G and you create this game G prime. The players in this game G prime, you want to check that they share a generalized history state that encodes an accepting execution of the original game G. So think about this, original game G. It's exponentially large, say, and sort of imagine, running this game as a quantum circuit. All right, so, you have. Let's see. So here you have the verifier of the original game G. It runs some polynomial time computation, and it'll send some messages to the first player and send some messages to the second player, and they do some arbitrary computation. They produce their answers and they send it back, and the verifier will finally do some computation to decide whether to accept or reject. So think of this as just being some quantum circuit, and we can apply the Feynman-Kitaev history state construction to this. in some way. And what this game does is it's sort of like a non-local games version of the Feynman-Kitaev circuit Hamiltonian applied to this quantum circuit that represents the big game. Okay? And it turns out if you do this, then you can shrink, this new game that you have is, logarithmic size. But there's sort of a lot of challenges that you have to deal with. The main difficulty that you have to worry about is that the prover's actions are arbitrary unitaries. Okay? They may be exponentially complex. But there is a way to, to run a game that checks that the players really do share a state like this. Okay. So our composable compression theorem improves on Jiangfeng Ji's results in several ways. The first thing is that the verifier complexity actually does get reduced, not just the question size. The main tool we use to do this is, we have a way of doing, performing succinct encodings of protocols. I won't talk too much about that. The other thing is, we avoid this blow up in the number of players by constructing a player merging technique. Okay. We also have a bunch of simplifications to his original protocol, and we also simplify the analysis a lot. Putting all of these things together, it allows us to create a compression theorem that is composable, one where you can sort of run it as many times as you want. So for example, our alternate proof of Slofstra's undecidability result requires running this compression scheme essentially an infinite number of times. Okay. All right, so let me say a few more words about this, our alternate proof. So, his theorem says that there's no algorithm to decide whether whether a game has entangled value 1 or not. And the proof technique is very interesting. So he reduces the word problem on finitely presented groups to the problem of computing the entangled value of non-local games. And the way he does this is he constructs games that essentially test group relations. Okay? And it's a very intricate and beautiful construction. Here we can reprove this result by using our compression theorem. And what we do is we sort of directly reduce the halting problem, or technically the non-halting problem, to the problem of computing the entangled value. And the intuition here is that we construct a game that essentially plays a compressed version of itself as long as a given Turing machine hasn't halted in a given time bound. So if you have a Turing machine that never halts, then essentially what this game will do is it will just continue playing compressed versions of itself forever. Okay. All right, so the thing there's a lot of pieces to this compression theorem, but the main thing that I wanted to highlight is our player merging technique. Okay. So, in this compression scheme, let's say we start with a 4-player game G, and the verifier V runs in poly of n time. Okay, so this is our original game. Think of it as being exponentially large. So the first step in the compression is you construct a 4+1 player game G, G prime, where the verifier V prime runs in logarithmic time, and you've introduced this 5th player we call P sub V, and we call it a trusted poly player. Okay, and what this means is when this little verifier V prime interacts with P sub V, it asks P sub V to perform poly measurements. So it'll perform poly X and Z measurements, and you trust it to do so honestly. Okay. And the rough intuition for what this piece of V is doing, it's essentially simulating, in some sense, the original verifier V. Okay, so you've sort of delegated this exponentially complex computation, the original verifier, to this prover. All right. So to remove this trust assumption, we use this idea of quantum secret sharing. So this verifier v prime interacts with this trusted poly player, but of course in non-local games, you don't have players that you can trust. To get rid of this assumption, what we do is we encode the original poly player using a 4-qubit error detecting code. So for example, if this original poly player had a qubit here, you encode it using this error detection code, and you split it and share it amongst 4 new players. Okay. And now you can get rid of this assumption for trust because you can use these existing rigidity theorems in self-testing results to ensure that these players not only perform poly measurements correctly, but they in fact do share a state that's encoded using the code you wanted. Okay. And now you just command, what the verifier does is command these players to perform logical X or Z operators. Okay. All right. So for the player merging step, so far what we've done is we've taken our original 4 players, we've added 4 more, and what we're going to do is we're going to combine them. Okay. And we combine them into 4 players again, so we haven't increased the number of players. And what happens is each of these players will pretend to be, so for example, this p tilde1 player will pretend to be the original player pi and also this added player pvi. Okay. And so this verifier, when it wants to interact with the original 2 players, it will send both of those questions to this merged player. And this merged player also has to send a pair of questions back. And the verifier will just check these answers just like in the unmerged game. And in general, merging players like this is a very bad idea because the whole point of a lot of these non-local games is you want to ensure that these these players can't communicate. So if you merge them, the merged player will get to see questions that was originally meant for 2 separated players. So how do you ensure that nothing goes wrong here? And in general, we don't know how to, we don't give a general player merging technique, but this is possible in our case because of special properties of the unmerged game that we constructed, and also special properties of the error correcting code that we've used. Okay, so I'm running short on time, but let me skip to. So that was just sort of a high-level idea of what's going on for the player merging technique. But let me end with sort of an interesting aspect of our compression theorem. So we can use it to prove some this complexity lower bound. And you might ask, is it possible that you can improve the compression theorem? So improve in what sense? So our current theorem has a trade-off between the size compression and the gap compression. So the verifier gets reduced from size n to log n, but the gap also gets reduced by a factor of n. So you might hope maybe there's a better trade-off, but it turns out that there would be some dramatic consequences to this. So suppose we had the following compression theorem where the verifier was shrunk exponentially, but the gap was reduced by a milder amount. So it went from epsilon to, say, epsilon to divided by n to the alpha. Think of alpha as like, say, 0.9 or something. Then it turns out we can actually boost this compression theorem to something that's much better, where the verifier still gets reduced from, say, n to the epsilon, but the gap stays unchanged. And the implication of this is that you can use this compression theorem to show that there's, deciding, approximating the entangled value of games up to a constant would be undecidable. And so that there would be no algorithm to do this estimation up to constant accuracy. In complexity theoretic terms, this would mean that this class MIP star would contain all computable languages as well as undecidable ones. And this would have ramifications for some questions in mathematics that people have cared about. So, for example, it would show that this would resolve Cyrilson's problem in saying that the tensor product model of quantum correlations is different from the commuting operator model. And this also verges on refuting something known as Kahn's embedding conjecture. Okay. And maybe the last thing that I'll say is that the reason it doesn't actually refute it is that the Kahn's embedding conjecture, its connection to games applies for games with only 2 players. Our results hold for 4, but it comes pretty close. Okay, so open questions. Can we improve our compression theorem? Can we reduce the number of players to 2? And maybe there are more applications of our player merging technique. Okay, thanks.
Any questions? So in your undecidability result, can you say anything about this number less than 1? You get 1 versus less than 1? Is it?
Yeah. So if there's a gap, then we don't know that it's undecidable. Yeah, the problem is if deciding between 1 and less than 1.
Yeah, just anything.
Yeah.
Okay.
I'm not very familiar with this field, but are there complexity theoretic results for whether or not the game has a quantum advantage, like higher than a Composable with classical?
Right. So we actually know with let's see. So one thing I should mention is that for classical games, we know that they are decidable. In fact, they lie in the class NP. And as for determining whether there's a gap, I don't know of complex results off the top of my head, but I suspect that's also pretty hard. Yeah.
Hey, I'm just curious about this magic number 4. Can you just give some intuition why it's difficult to go below 4?
Okay, so I think that there should be a way of reducing the number of players to 3 using a different error correcting code. Yeah, so essentially what we use is what we really need is an error detecting code, and we know of those with tripartite error correcting codes, but I don't think there's exists with just 2 parties. So I think maybe that's the main bottleneck. Yeah.
Any other questions? Okay, if not, let's thank Henry again.